The amount of energy humans use in a year is equivalent to an hour's worth of sunlight striking the Earth. Sunlight is a renewable source of energy. Natural systems, such as plants, harvest solar energy to power their lives. We too can harvest the sun's energy in a variety of ways, from low-tech to high. One high-tech method uses solar cells to generate electricity. When sunlight strikes certain materials, it produces small amounts of electric current, a marvel called the photovoltaic effect. The current can then power electrical devices, from light bulbs to electric cars. The ability of a solar cell to operate is based on a material called silicon. Silicon is the second most common element in Earth's crust. In the periodic table of elements, which illustrates recurrent trends in the chemical properties of elements, silicon resides just below carbon and shares many of carbon's chemical features. The dot diagrams shown here display key features of silicon and several surrounding elements from the periodic table. The dots represent the number of negatively charged electrons that each atom has in its outermost shell. Called valence electrons, these are the ones that participate in chemical reactions. Notice that carbon and silicon each have 4 valence electrons. Boron and aluminum have 3, and nitrogen and phosphorus have 5. By sharing valence electrons, a silicon atom can bond with 4 other silicon atoms. In this way, the central atom essentially achieves a full outer shell of 8 electrons. Because a full outer shell is a more stable configuration, atoms tend to bond with other atoms in ways that achieve this state. Thus, silicon atoms join the group to form a large silicon crystal. Silicon crystals form the basis of solar cells. Because it has a somewhat loose grip on its valence electrons, silicon is considered a semiconductor. At any one time, a small number of the silicon atoms in the crystal gain enough energy to eject an electron, leaving behind a positively charged hole. The electrons and holes soon recombine, while newly ejected electrons repeat the pattern. If a voltage is applied to the crystal, the free electrons and holes migrate in opposite directions in the electric field toward oppositely charged poles. This migration represents a relatively small current flow. In contrast to silicon, a true conductor such as copper has a much looser grip on its electrons, and with a voltage applied, a relatively large current can flow through a copper wire. In a solar cell, a silicon semiconductor is made so that it has specific impurities, resulting in what is known as an N-type side and a P-type side. In the P-type side, some of the silicon atoms are replaced with boron atoms. Boron has only 3 valence electrons. A 4th valence electron doesn't exist for boron, leaving a hole in the crystal. Therefore, 7 rather than 8 electrons are shared among boron and the surrounding silicon atoms, an arrangement that is inherently unstable. Similarly, the N-type contains phosphorus in place of some of the silicon atoms. Phosphorus has 5 valence electrons. In the crystal, a phosphorus atom has an extra unshared electron that disturbs the uniform structure of the crystal and is an inherently unstable configuration. The impurities and resulting instabilities are essential elements of a solar cell. At the p-n junction, the extra electrons from phosphorus attempt to fill holes in adjacent boron atoms. In this way, electrons flow from the N side to the P side. As an electron leaves a phosphorus atom, it leaves behind an unbalanced positive charge on the phosphorus atom. When the extra electron moves onto a boron atom, it brings with it a negative charge. As the positive and negative charges separate from each other, an electric field or voltage develops at the junction, which is now called a depletion zone. An electric field of this sort is always present in a solar cell. Now consider that our solar cell is in a circuit with a device, such as a fan. When photons of light strike the crystal, the energy may be enough to knock the loosely held electrons off the atoms. As a result, negatively charged free electrons leave behind positively charged holes in the crystal. The free electrons will attempt to fill available holes. This may occur in a few different ways. For example, electrons may simply recombine with adjacent holes in the N layer. Alternatively, electrons may attempt to fill the many holes in the P layer. However, the bank of negative charges on the P side of the depletion zone prevents the negatively charged electrons from passing directly through. The depletion zone is thus a one-way path for electrons, an essential feature of a solar cell. In contrast, electrons can flow through an external circuit to reach the P side. As electrons travel in one direction, the holes travel in the other. As electrons move through the circuit, they provide power to electrical devices such as the fan shown here. In this way, light energy can be converted to electricity.